Okay. Hello, Emma. Welcome to the prototype of the Earth Sciences podcast.
Hey, how are you doing?
Good. So with my brief bit of research on what you do in your research, my summary is that you develop custom-built drones to fly around volcanoes, and you do this all over the world, which sounds amazing. Is this correct?
Yep, that is pretty much what I do right now.
Excellent. So, what's your current project? What are you currently working on?
So my most recent project has been actually in the South Sandwich Islands. So somewhere completely remote, somewhere about 500 miles from any civilization, but there's this beautiful chain of volcanoes there called the South Sandwich Arc. And I was very lucky to have the chance to take an expedition there. I could tell you a little bit more about that if you want. But basically we were there to measure the volcanic gas emissions. So there's been very little work done on this arc. There's been a little bit of petrological work, so some looking at kind of the rock genesis, but no one's ever made any measurements of the volcanic gases, how much carbon dioxide is being released, and some of these volcanoes are really active. So we used a combination of some of the drone technology we've developed over the last few years to access some of the inaccessible regions, but then also some traditional ground-based techniques to collect physical samples of the gas to bring back.
Great. Where are the Sandwich Isles? I haven't heard of them before.
So they're in the subantarctic, right at the very south of the Atlantic Ocean. So if you think about the base of South America, they're in between the base of South America and Antarctica in the Drake Passage.
I've heard the weather there is rough. That kind of part of the world's quite wild. How was being there? 'Cause I've never done any field work myself, so I'm always in an office on a computer. So it always kind of fascinates me. So what's it like to actually go out there and?
It was quite an incredible place, and I admit already we were very lucky with the weather. So before I went, I was warned that, I mean, we had to get there on a boat, a very small boat. And I've heard stories about the Drake Passage, and I'm not very good with seasickness. But actually, it was rough. It was stormy, but we didn't have any major storm systems coming through. So we sheltered for a few days behind, like in the leeward side of some of the islands, to let some bad weather pass. But when we got back to Stanley and the Falkland Islands, and everyone asked us how it had been, they were all amazed that we'd had such a solid weather window down there, because that's very rare.
Hmm. I also wonder, like, how long are you out there? Because I guess one of the things with field work, I imagine, is you're only got a limited time window, and so there's a lot of pressure to kind of get it right and for things to work.
Yeah,
So
no, you've got it bang on. So the entire expedition was 6 weeks, and for 5 of those weeks we were on this small boat of 14 people. But actually, the amount of time we got at each of the islands was tiny. So we actually only spent 9 days on scene on the South Sandwich Islands. The first part of the expedition was South Sandwich, and then the second part was South Georgia. It was quite a multidisciplinary team. So we were Team Volcano. We had glaciologists, penguin ecologists, and everybody had slightly different kind of roles and data they wanted to collect. But I mean, in those 9 days, we were able to make 6 shore landings. And even some of those required swimming ashore. And when we were ashore, we would then get, I mean, on Saunders, we were lucky we got full 12-hour days. But other islands, it was a 3-hour get in, get out quick. And it was all very well for the teams who worked on the beach where we landed. They were surveying the penguin colonies. We often had a 3 or 4 hour hike into the interior of the island where we would take our gas measurements. So by the time we got there, we were being hassled on the radio to get going and get back again. So I actually found the pressure of time ashore really quite stressful, especially as I was using some new techniques for gas sampling that I wasn't familiar with. So I was learning something new.
yeah, what were some of the techniques? I mentioned your research. You've highlighted some of the drone work you've done, but and I'd be interested in hearing more about that. But like, what are some of the tools and techniques you use?
So when we're measuring gas emissions, there's different pieces of information that we want to know. We want to know the chemistry. So what proportion of different gas species are in the plume? So the main elements we're looking for are carbon dioxide, sulfur dioxide, water, and then sometimes we can get minor species like hydrogen fluoride, hydrogen chloride. So we want to know the chemistry. We also want to know the emission rate. So typically in kilograms per second, what is the emission rate of SO2 coming out of the volcano? And we also want to know things like the carbon isotope composition, because they will help tell us not just how much gas is coming out, but where the gas originally came from. Was it from the mantle, or is there a roll from the subducting slab? So we measure these kind of three different pieces of information in very different ways. So for the chemistry, we use a small sensor called a multigas. It does what it says on the tin, multiple gas analyzer. And what we've been working on over the last 3 years is to miniaturize this multigas from a 3 kilogram large box that's designed to be used on the ground into a 500 gram small modular payload that we can mount on a multi-rotor drone. So this is probably the technique I'm most familiar with, and we've done this inaccessible volcanoes all around the world. But we would mount this multigas on the drone, and in this case fly directly upwards between 500 meters to a kilometer up in the sky to intersect the main part of the gas plume that was being blown. So we would typically spend maybe 10 to 15 minutes in the plume gathering data.
And does that mean slurping in the gases into the machine?
Yes. So it's all a pumped system. So there's a little inlet and a pump sucks in the plume. It goes through the CO2 spectrometer, through all the electrochemical sensors for sulfur species, and then gets spat out the other side.
Oh, great.
But that gives us the chemistry. But what we really want to know is how much is coming out. And we use that by something called remote sensing. So we use a UV camera. So this is something that we mount on the ground, and it looks sideways again at this horizontally transporting gas plume. And it uses spectroscopy. So it uses the light from the sun and how much of that light is absorbed as the sun's rays pass through the gas plume. So different gas species absorb at characteristic wavelengths. And the only one that we can resolve robustly is SO2, because it's negligible in background atmosphere. Carbon dioxide and water are really hard to measure spectroscopically. So what we do is we set up this UV camera to measure the emission rate of sulfur dioxide. And then if we know the chemistry, so the ratio of carbon to sulfur, for example, we can then derive the emission rate of carbon dioxide, which is kind of the holy grail of what we're trying to do in a lot of my projects.
And why is that? Why do you want to know the CO2 emission rate?
So I've been involved for the last few years in a program that's been going for about a decade now, called the Deep Carbon Observatory. And kind of the role of this organization was really to delve into all the different aspects of the deep and shallow carbon cycles. So how does carbon move through the mantle reservoirs? How is it transferred from the mantle to the atmosphere and ecosystems by things like volcanoes? And part of that was we realized as a community that our uncertainties on global data sets like carbon dioxide emissions was hugely lacking. And a lot of those gaps were due to not being able to access particular volcanoes, either because of their remote location, steep terrain, or high level of activity. And this is where the drone work started to come in, and we've been gradually filling in a lot of our gaps in our knowledge through using established instruments, but in new ways.
So I guess this is, because back in the old days, you would have to walk yourself up to the place, plop the system down. Because you're describing earlier flying through the plume. I mean, I imagine that'd be pretty dangerous if you were in the plane or whatever it is that's flying through.
Yes, so you wouldn't want to be in a manned aircraft for sure. So when I first started making these measurements, I was still hiking up to the crater rims, placing these multi-gas instruments directly in the plume. And actually, at the beginning, when we were transitioning into kind of drone-based operations, we'd be doing a compromise. So we'd hike maybe 4 or 5 hours up to the summit of some volcano, such as Villarrica. That was one example that I did. And we would fly from the crater rim down into kind of the lava lake, the open lava lake that was there. So one of my first studies using drones was, I still think quite an elegant study. We combined 3 different techniques in tandem to try and kind of validate these new approaches. So we had super proximal gas measurements from a drone flying directly over the lava lake. We then simultaneously had an established multi-gas station on the crater rim that would be typical of operational monitoring. And then we had a UV camera stationed much further downwind, maybe 5 kilometers away. So we saw some interesting atmospheric processes going on. So we saw that even over distances of maybe 100 to 200 meters, so between the surface of the lava lake and this crater rim, we got huge amounts of dilution and mixing. So when we flew the drone over the lake, we could see this remarkable periodicity that we could correlate with discrete bubble bursts from the lake. But by the time the gas plume had reached the crater rim, it had homogenized and reduced in concentration so much that the structure was completely absent. So we actually learned quite a lot about what happens in that very early stage of plume interaction with the atmosphere. And a lot of that is controlled by crater geometry and how much turbulence and mixing happens.
Yeah, so it sounds like drones are opening up a lot of stuff that just simply was impossible before.
Yeah, I mean, it's been a remarkable journey. And it does seem to be that drones are accelerating into all aspects of geoscience. They are particularly suited to those fields that either require surveying over huge areas, where a survey would take somebody months to years, or into very inaccessible, hazardous areas. There are still a few challenges, though. They're not the solution to everything. So a problem that we're finding now is that when we're really pushing the frontiers of beyond visual line of sight flights, so we're maybe 10 kilometers away from us, 2 kilometers up in the air, we're very limited by the amount of time we can spend in the plume. And when we're using fixed wing vehicles, we can't hover. So it's typically a series of very rapid traverses through the gas plume. But each of these sensors that we have on board, they have a response time. So what we've been finding is that if our transition through the plume is too fast, our sensors can't equilibrate. So actually, as we transition into solving some solutions, new problems present themselves. So it's an endless cycle of discovery.
Mm. So I remember I was reading through skimming through one of your papers, and it mentioned that you developed a drone yourself. It's like, I think, a 6 or 8 winged drone that you used in your recent study. Like,
yes.
Could you describe this a bit more detail? I'd be interested to hear like what the actual kit is and what it can do.
So we're somewhere between a custom built and an off the shelf. So I collaborate very strongly with the aerospace engineering department at Bristol University. So a lot of the credit I must send in their direction. But we typically use commercial components. So we'll maybe use a commercial frame, and then we'll customize it with our own avionics, so own flight computers, different motors, different propellers, to kind of get the optimum balance for the payload that we want to mount. And often these frames are not designed to carry any payload at all apart from a camera. It's only really been in the last few years that people have tried to put actual instruments on drones, although they've been around for a decade or so for imaging.
So how big is it, and does it have a nickname?
All right, we've got quite a collection. So our smallest one is about this big, about 30 centimeters long. That's the very smallest one. And the biggest one is a glider, which is a 5-meter wingspan glider. The ones we use most are quadcopters, so 4 rotors, and that's typically about 1 meter from blade to blade. And they're a good compromise between portability, because we normally have to carry them on our back, and being able to carry something slightly heavier.
Yeah. How do you launch a 5-meter wide drone in the field?
Those particular ones are hand launched. So they're super light. And yeah, you power them up and they kind of just launch out your hand. The power of the propellers just needs a very slight input from the hand to send it in the right way, but really it's got plenty enough thrust. It's way overpowered to get up into the air. And then we typically throttle back and let it do slightly more gradual zigzag ascents.
I know. This has all been very interesting. Yeah. Oh, I guess. Yeah. What got you interested in earth sciences and volcanoes in the first place? Like, how did you get to traveling to the far end of civilization?
So my interest in volcanology actually started a very, very long time ago. I was a small 6-year-old, very impressionable 6-year-old, and I was introduced while I was on holiday into the States, and we went to see Mount St. Helens. So although it was long after the eruption, I could see all the trees were still down, being blown and blasted in one direction, and the landscape was just like nothing I'd ever seen before. And I don't claim I fully understood at age 6. I had no idea, but I was fascinated, and that stayed with me. So when I started kind of in my teens learning more about geography and how the world works and how natural hazards interacted with society, volcanoes was a natural direction that I wanted to follow. And then I did a 3-month internship at the Montserrat Volcano Observatory during my undergraduate degree, and that cemented everything for me. That was working in an operational monitoring environment with scientists who knew the ins and outs of their active volcano in like no one I'd ever seen before. And yeah, it was inspiring and really cemented the idea I was then going to go on to do a PhD and stay in academia.
Cool. And I guess a final, unrelated question. What's something you'd recommend people check out? Like, as this is unrelated to earth sciences, like a book or film. Is there something that's kind of got you through this lockdown?
Yeah, okay. So it's completely not earth science related, although the lessons in it I think are definitely transferable. So I'll get it. It's right behind me. And I swear I didn't plant it. I didn't know this question was coming.
No, you didn't. I sprung it on you.
So it's Ant Middleton's book.
Mm-hmm.
So Ant Middleton is an ex-SAS soldier, and I picked up his book at the start of lockdown because I, for better or worse, applied to go onto his SAS program. We don't know whether I got onto the TV yet, but I thought I'd read his biography to learn about some of his experiences in the SAS. And I found his book incredibly inspiring. He frames a lot of his experiences in terms of kind of learning lessons for leadership in business, in industry, and personal relationships. And so I definitely recommend checking it out because it's made me view kind of team dynamics in a research environment as well, in a completely different way. So it's also very well written and super interesting. He's a very interesting guy. So check it out.
Cool. What's the name of the book?
Ant Middleton, First Man In.
Cool. Wow.
I get a commission for every book.
All right. Well, thank you very much, Emma. I think this went pretty well.
Great. Lovely to chat.
Yeah. Ciao.